Okay, so we're shifting gears a little bit here. The last topic in this chapter is interferometry. So it looks like we are still okay in the chat. Ask me a question on mic anytime you want to. So we've spent some time talking about like optical devices and how they're used in practice, be it a microscope or a telescope or really anything that involves light passing through some aperture. This is something that you can also, or I should say the concept of light being, or the principle of superposition as it relates to light. So we can add two displacement functions to see how light interferes with itself or really combines with itself. You can make use of this or like exploit this property so that you can take a kind of modest quality signal and add it to itself so that you end up with something that's a little bit more detailed than what you would get if you weren't using interferometry, if you weren't splitting the source apart and then rejoining it in a way of your choosing. So this is something that has a real life scientific application in I'm thinking of all the examples that show up in astronomy and physics, but it's something that you can also kind of demonstrate with a sound wave. So imagine that you've got a sound source here that you are feeding into some sort of structure where the structure is going to kind of impose limits on how the wave will interfere with itself in a way that's kind of similar to the tubes that we talked about in the second half of the superposition chapter, where we know that a tube, if we know the length of that tube, we can figure out which frequencies will cause nodes to form in which areas on the interior of that tube. So instead of worrying about how the wave is interfering with itself, like in the beginning of this process, imagine that we could just feed a sound wave into this structure. There is like a fork in the road here where some of that light is going to just go directly toward the microphone or some of this sound, I mean to say, is going to go toward the microphone that's collecting it. Some of it's going to take this path here. So the part that ends up taking this path is going to be constrained by by this upper tube here. And it's going to travel physically a longer distance to get from the loudspeaker to the microphone. The part that doesn't split off at all just travels this distance r sub 1. But the part that takes the longer path is going to have to go up this distance up this distance L, over this distance lowercase a, and then back down L. So we can figure out the path length difference for the portion of the sound that takes the longer track. It's going to be 2L different than whatever the portion of the sound wave that just takes path R1 is. So this A plus B is going to be common to each one because B is the distance between the point where the sound wave recombines and where it's collected by the microscope. And then A is the width of this little section here. They're both traveling that. But this 2L is going to be our path length difference. So the path length difference, delta R, that has to abide by the same rules that we encountered for the first time in the previous chapter, so that when the path length difference is some half integer multiple of m, you're going to end up with destructive interference. So a maximum and a minimum adding together to give you nothing. And whenever the path length difference is an integer multiple of lambda, you're going to end up with constructive. So either peak added to peak or trough added to trough, but nothing is canceling, everything is adding together. So if we know that, let me go back to this image here. So capital L is like the vertical part of this trip. It's only being traversed by the portion of the wave that is taking the longer path here. So if we can, if we can adjust or design a device where L is guaranteed to be some integer or half integer, as the case may be, multiple of the wavelength that you're looking for, you can kind of go back and forth between scenarios where you have very little interference or you observe very little interference, and then scenarios where you observe a whole lot of interference. These images are not a perfect companion to the discussion that we're having now, because there's for the interferometry, you don't actually have two individual sources. You just have one source that you're splitting and causing it to add together in a manner of your choosing. So the I guess the equivalent of the airy disk for that sound wave would always have the same shape, and it would be circular. It wouldn't be oblong like this. But the point that I'm trying to draw your attention to here is the amount of interference. You can go back and forth between lots of interference and very, very little interference. Okay, so this is something that you can observe with an interferometer. There are a lot of different physical devices that work with this this principle. The gravitational wave detector, LIGO, L-I-G-O, works with this basic design, but the earlier forms of interferometers were ones that kind of look like this simple diagram here, where there is some source that you're trying to observe. You've got two mirrors, one that you can move and one that you can't, so that the fixed mirror here is always going to be the same distance away from this beam splitter. The beam splitter can be thought of as being kind of similar to those two-way mirrors, where some light's going to pass straight through it like an ordinary window. The rest of it's going to reflect the way that an ordinary mirror would be able to reflect it. So instead of our sound source that we're splitting up and causing it to travel two different paths, we have a light source that we're causing to travel two different paths. And there's like an eyepiece that you could put your eye to observe whether you have a whole lot of dark fringes or a very small number of dark fringes. That will change based on how you change this distance L2. So let's trace this, where we have some light from the source that hits this beam splitter, and let's just track the portion that starts off being reflected first. So it's going to interact with the beam splitter as if it's a mirror. It's going to reflect a portion of that light source toward mirror one, where mirror one's job is literally just to reflect that light the same direction from whence it came. So that now you've got these two waves that are going to, well, the portion of the light that we're talking about now is ultimately going to add back with the portion that we're going to talk about in a moment. So this one path here, it goes to the beam splitter, up to mirror one, off of mirror one. The second time it interferes with the beam splitter, it's going to act just like a window. It will transmit. So it's either reflection first, then transmission, or the opposite direction, or the opposite order, I should say. So let's look at the portion of the light that goes from the source. It doesn't reflect off of the beam splitter, but instead just fully transmits through it or passes through the first time. It's going to interfere with mirror two that you can set at whatever position you choose. And now when it interferes or when it interacts with the beam splitter the second time, it's going to reflect. So that you've got one source that reflects first, then transmits. The other portion is going to transmit first, then reflect. So that they are now adding together. You can put your eye to an eyepiece and see something that looks like the slides from our Rayleigh's criterion discussion a few slides earlier. So the entire reason behind being able to adjust the position of the second mirror is so that you can change this value L2. So that if L2 is such that you are going to essentially cause the beam that's joining up again here on the opposite end of the beam splitter to either add in a way that will cause constructive interference or destructive interference, where a peak and a trough add together, you'll be able to actually detect that change with your eye, looking at what the pattern looks like. And this is a Michelson interferometer. This is the same Michelson from the Michelson-Morley experiment. And I think I have an additional A that doesn't need to be here. That's just current slide here. This is the appropriate way I'm certain to spell Michelson. So this experiment, there's a kind of cool long story that's associated with this device here that actually involves, I don't remember whether it was Case or Western Reserve before they joined together to Case Western as they are now. But these two scientists, Michelson and Morley, were based right here in Northeast Ohio. And they used an interferometer like this to try to figure out what material light travels through. So to kind of take us back to our first chapter, traveling waves, we talked about mechanical waves, electromagnetic, and then matter waves, where electromagnetic waves didn't need to travel through a medium. They can travel through a medium the same way that you can still see if you open your eyes when you're underwater. So light's traveling through that water, but it's also perfectly capable of traveling across the vacuum of space. It doesn't require a medium. So at the time that Michelson and Morley were active, so we're talking like mid to late 1800s, they were trying to figure out what light travels through. We now know that the answer is that light doesn't have to travel through anything. But the assumption that they made was that light has to behave in a way that's kind of the same as a sound wave or a water wave, where it has to go through something. So their hypothesis as to what this something was took into account the fact that if there was indeed a medium, it had to be really hard to detect, because otherwise the answer would be obvious to us. And two, they were functioning with this type of interferometer. So assuming that they could isolate whatever, or really just identify the material that light moves through and force it to interfere with itself, that causes it to either add perfectly or subtract perfectly. So their first crack at this, and I want to say 1881, but you can fact check me there in case I'm wrong. They suggested that there was, or they hypothesized that there was some material that was hard to detect called luminiferous ether, whose job was just to move light from one point to the next. And they figured that if you use the sun as an example, if light has to come from the sun's surface and traverses space so that we can observe sunlight here on Earth, then there should be two different points in the year where we can catch our planet either plunging directly into this quantity of luminiferous ether or moving against it. So to say that another way, imagine that you are in a wind tunnel and you have the option to either run with the wind or against it. That's kind of what they were looking for, but instead of a person running, it's Earth orbiting the sun. So they figured that if they took two measurements at different points in the year, they should be able to catch Earth going exactly with the ether and exactly against the ether, so that they could figure out the properties of this ether. And again, we know that this is not a thing that exists now, but the 1881 Michelson-Morley experiment did not detect any luminiferous ether at all, because it's not a real thing. We know that now from our perspective, but they did it. So the way that they responded to the failure, or the data that they collected that did absolutely nothing to prove that there was such a thing as luminiferous ether, they figured that their interferometer was just not complex enough. So if they introduced like multiple mirrors, some of which could be moved, some of which were stationary, they could really kind of slow this light down, or cause it to spend a lot of time bouncing back and forth inside of the interferometer before it's added together and then observed by whoever has their eye to the eyepiece. And I have an image of it in a different PowerPoint. If anyone's interested in it, let me know, and I can kind of isolate those images as opposed to making you wait for me to search for it here. But it's just like this same idea, but just way more reflections, way more complicated, much more time that light would spend bouncing around in the interior of this device. So the second time around, I believe 1887, is when they redesigned. They figured that they were going to recollect or retest so that they could identify this luminiferous ether. We know that they found nothing again. And the results of that second test led them toward the conclusion that luminiferous, or they had no evidence whatsoever that luminiferous ether existed, but they did have evidence that light could only travel at a specific maximum speed, or in other words, that it had an upper speed limit to it. No matter how many times they tried to bounce that light around in their really complicated interferometer, it was still traveling with a predictable speed, or one. They couldn't speed it up past that point. And really, they didn't really have the capability to recognize how much light had slowed down, because they were conducting these experiments on Earth's surface, so they didn't have the benefit of working in a vacuum or anything like that. But the light that was traveling through Earth's atmosphere was all moving at pretty much the same speed. So they ended up kind of stumbling onto a fundamental truth about how the universe works and how light works, even though they made, no progress whatsoever on finding what light actually goes through. So this image here kind of shows one of the possible images that you would observe if you were to set up even a simple interferometer like the one that we just talked about a moment ago, and change the position of your movable mirror so that you can either have a bunch of dark fringes that show up or a minimum number of dark fringes. And we're still trying to relate this back to the concept of path length difference. So if we're trying to look at the difference between, and I think L1 was the path, the larger path here. Yeah, so so L1, or not the larger path, but this is the fixed path, the one that's the same no matter what. You can change your L2 so that you either end up with a half integer multiple or a full integer multiple of lambda. And this last question here lets us put this into practice. So probably don't have enough time to do all of this right now, so I can start with this at the beginning of our next lecture on Monday. But if you know, not even the change in position for your movable mirror, but just the number of dark fringes that show up and the wavelength of the light that you're observing, you can figure out what delta L2 would have to be. So imagine you adjust the screw so that L2 gets a little bit larger. You can just look at the pattern that results and figure out how much the mirror moved, because that's something that is a lot easier to calculate based on what you observe, as opposed to measuring directly with a meter stick or some other device, because it's going to be an incredibly small change in position that results in an image that either looks like this one here or one that has far fewer dark fringes. So we'll do the actual problem solving next time, but just a last kind of idea to end on. This is something that's exploited a lot in, especially in the field of astronomy, because of the limitations that you would find if you were in charge of building a large telescope somewhere on Earth's surface. So a radio telescope or like a satellite dish, because radio wavelengths are so long, satellite dish or radio telescopes have to be pretty big in order to have any quality of resolution, where you can take that to mean the level of detail that you could see in an image. If you took, let's say, a pair of binoculars and looked at the moon, the level of detail that you would be able to see would be much less than if you had like a 1 meter telescope or if you went to an observatory. So you're looking at the same thing, but the device that you're working with is limited. Not all that different from the discussion that we had with uncertainty in our wave optics lab. So practically, if you're trying to build a radio telescope that will produce high resolution images, you need it to be really big. And the largest ones on Earth's surface, I want to say, are like 300 meters or so in diameter. But even figuring out like where to place a telescope like that and how to fund it, that can be a real challenge. But interferometry kind of lets you get around that by, instead of having one enormous telescope, you can have a larger number of modestly sized telescopes. So these could be maybe 10 meters in diameter, but the more of them you have, the more of them, or the more signals you can add together, basically. And the idea is that if you have these telescopes aimed at the same thing and placed a certain distance apart from one another, when you recombine the light from, or when you combine the light that comes from the two individual scopes, you end up with an image that is as detailed as one that you would collect if you had a single enormous telescope. And there are a few different examples of this. There are some visible light telescopes on the Mauna Kea in Hawaii that use this same idea, but it's a lot more common with radio telescopes. And this image here is the VLA, the Carl Jansky Very Large Array. That's just a whole bunch of somewhat kind of medium-sized, I guess, 25-meter radio telescopes on train tracks that you can either spread way out or pull inward. And when they are spread out, and each one of them observes the same thing, when you put together those signals, you end up with an image that's on par with one that you would, or that would be possible to collect with a 22-mile diameter telescope. So one that's never going to be built anywhere on Earth's surface because it's unfeasible for many different reasons. But you end up just kind of exploiting this property of light and ending up with a really detailed high-resolution image. And this is kind of similar to what was used back in the late 60s for the like imagery of the moon landing and stuff like that, that the raw video, or like the highest quality video from that, is lost, I think. But basically what was used to produce those kind of like ghostly, like translucent looking images of astronauts on Earth, or the moon's surface, was this same idea, but telescopes that were based like in Australia, combining with ones that were based in the States, combining with ones that were based in South America, all collecting the same thing and then joining that image together. And I think the VLA is in like one of those later Terminator movies, playing Skynet, the ones that you can mostly ignore. But I'm over the limit here, so I'm going to stop talking. Do you have last minute questions? Okay, so we have just one problem to go through from the end of the wave optics chapter. Then we can jump into ray optics. And let me grab the second half of our presentation just to get us kind of resituated from where we left off on Wednesday. Okay, wave optics is what we want. Okay. All right, let's start sharing. You should be able to see that in a moment. Okay, so the last topic we discussed on Wednesday was the topic of interferometry. So just to kind of get us back on track, an interferometer is something that can take a single light source and split it up so that you can force it to add back together in the manner of your choosing. So if you want to take a source or a light that comes from a single source and split it up so that it interferes destructively, you can achieve that by adjusting this movable mirror. Or if you want the opposite, which is kind of what's shown here, you want it to add together constructively, you can, well, both of those outcomes are achieved by moving this mirror here. There is a beam splitter that kind of acts like a like a one-way or maybe a two-way mirror. I don't know what the correct term is for that device, but some of the light is going to interact with the beam splitter the way it would interact with a mirror. So it's going to reflect up along this path here. The rest of it is just going to transmit the same way it would if it was just passing through a window or something like that. And then it will reflect over here. The second interaction of the beam splitter is always going to be the opposite of whatever happened the first time. So for the portion of light that transmits first, the second time it interacts with the beam splitter, it's going to reflect, and then vice versa for the portion that reflects first. And if you were to put your eye to an interferometer or a Michelson interferometer specifically, what you would see is something that looks either like this case here, where, and just to kind of backtrack, this is an example of circular aperture interference again. So what you see here is a bunch of dark fringes that are superimposed over what otherwise would be just a solid kind of disk of light. And this M value relates to the number of bright fringes that form as a result of these dark fringes being superimposed on top. So we are looking for, in this case here, constructive interference. So this is going to be when M is or I should say lambda is multiplied by some half integer number M. And if we were going to look for the opposite case where we wanted destructive interference, we would look for the integer multiples of lambda. So let's see. I accidentally let my tablet drain all the way down. So I'm only at like 2 or 3% right now. So instead of working this out in real time, I'm going to go back to a scan that I had from a previous semester. So I'm going to stop sharing here and grab this file in my other window. We can still talk through it just like we do normally. Okay, so now should be able to see this here. So a scan of example number 5. And the scenario that we're trying to make sense of is one that involves a Michelson interferometer. We are adjusting the position of mirror 2. So not to jump back and forth between programs that I'm sharing here, but if you go back and look at our notes for the method that we can use to find the number of bright fringes, we find that it's the total delta L that we're concerned with. So there's an L1 that is the path between the beam splitter and the mirror that you can't adjust. And then L2 is the distance between the beam splitter and the one mirror that you can adjust. So L1 is always going to be the same thing. So delta L is always going to be the result of you adjusting mirror 2. So in this case here, we don't have the value of L1 or L2, but we know the wavelength of the light that's coming from the source, 480 nanometers, and we know the number of dark fringes that show up in the field of view. So the fact that there are bright fringes there means that you are observing some level of destructive interference. If we were to trace a nodal line from the beam splitter to the eyepiece, in this case here, we'd be able to find locations where the light adds together in a manner that causes it to perfectly cancel out. So since we know that there are 150 of those, the value in the interferometry expression, actually this one down here, we can take a look at. The value that we would plug in there would just be the mode, so like the M value for the interference pattern that we're observing. So if we know that M is 150, we know the wavelength of the light source that we're viewing. What we're trying to find here is how far the mirror moved, but since L1 is always constant and L2 is the one that changes, even without knowing the value of L2, we can figure out how far that second mirror had to have moved. So all we have to do here is just kind of plug and chug. We have our half wavelength multiple multiplied by the number of dark fringes that you can observe. And what we end up with here is 3.60 times 10 to the negative 5 meters. That would be 36.0 micrometers if we were sticking to sig figs. And we've got we have just 2 of them to work with here. So this should just be 36 without the 0.0. So that's a change, and I can get rid of this little typo here. But once I have enough, I guess after we get out of lecture, after I get out of my 10 o'clock lecture, I can just put this into the file that's going to contain, or that already contains, the rest of our wave optics solved problem, so that you don't have to go back and forth between this old scan and the way that we've been handling our class notes up until now. And hopefully by the time we get to our first problem in the ray optics chapter, I'll have enough juice to kind of do this in real time. Okay, let me stop sharing there. I'm going to go back to our notes. We ended our discussion last week with a discussion of how you can apply this to, instead of one device observing a single source, if you get a bunch of devices to observe the same source, you can add all their light together and you end up with an image that has the level of detail or the angular resolution that is equivalent to what you would get if you had a single large or single enormous telescope. So one that's, too big to actually practically build anywhere on Earth's surface. And we use the VLA in New Mexico as an example of how you can actually put this to work. So you've got a bunch of kind of modestly sized radio telescopes that can be either stretched out or pulled inward. They're all on railroad tracks, essentially. And at the largest separation, when you add all the light together from these individual radio telescopes, you end up with something that has the resolution that matches, or that would match, a single 22-mile diameter radio telescope. So I know we talked some about the Michelson-Morley experiment and how that the first couple of iterations of that failed to detect what Michelson and Morley were setting out to find, but instead they kind of indirectly or as a bonus maybe confirmed that light has a maximum speed. It was really the first good measurement of, or maybe not even the first good measurement, but the first good evaluation of C that was achieved. So this again is like the late 19th century when this is going on.